Hi students, welcome to my lectures. Please follow my earlier lectures on DWSIM in this DWSIM playlist. So far we have discussed about uh, how to estimate energy requirements and temperature measurements in adiabatic compressor, and subsequently I have shown one more simulation, that cooler or heat exchanger. Further simulations mainly uh, these are very easy. It's a single click answers from the DWSIM, whereas if we cross verify with the hand calculations, and it will be more as such a kind of small tedious kind of work, but no matter, I have made the things very simple. So in this lecture we are going to discuss about finding the volumes play very important roles. As far as, if you remember, an ideal gas equations PV equal to RT, you can estimate the volume, and whatever the volume you compute based on the equations, it is based on the assumptions that there are no intermolecular attractions between the molecules or molecule having negligible volume. These are the inbuilt assumptions where the ideal gas equation has came up with. But in reality, we have to deal with real gases, that means non-ideal gases. The prediction of non-ideal volumes play a very important role. For example, uh, as far as chemical engineering is concerned, we talk about many situations where we have to estimate how much amount of separation is possible, how much amount of purification is possible, how much amount of reaction that is possible. All the things requires uh, some parameters. Okay, in parameters, volume is one of the main important parameter, based on which you can able to estimate the separation capacity or purification capability or reaction. How much, these are the things. Okay, the parameters which are easy to measure is temperature, pressure and volume. Okay, so volume, temperature and pressure we can able to measure, based on this temperature indicator or pressure indicator kind of. Volume you have to estimate. Okay, just like in ideal gas equations, there are many other equation exists. These are called equation of states. That means a prediction of a state. In a state, any molecule occupies a certain volume or certain property. Volume is one of the property kind of, you can imagine. Okay, there are many equations proposed in the name of equations of state. One such an equation of state is a Soave Redlich Kwong equation of state. Okay, because because in today's session we are going to use this Soave Redlich equation, Redlich Kwong equation of state, SRK equation, that means SRK equation of state, to compute the non-ideal volume of a gas. And we also compare with the ideal gas volume, so that you can able to judge what is the difference between these two. So today entire thing is focused on finding out the volume. So let me take you that how we are going to approach. Okay, you can observe here, estimation of vapor volume. The volume you are going to measure is a molar volume. Okay, in centimeter cube per mole using SRK equation of state. In today's example we are going to take n-Butane as an example. So what we are going to do is we take some material stream. Okay, and apply Soave Redlich Kwong equation of state to find out the to find out molar volume, which is around 5300 centimeter cube per mole. That means n-Butane occupy at 76.85 degrees centigrade and 5 bar. Okay, at this conditions we are able to find out what is the volume occupied by this n-Butane gas. Okay, so for that you need have information about in terms of DWSIM. We need to, because all the things or calculations are per mole basis, so molar flow rate we are going to mention is 1 mole per second. Okay, and accordingly you keep 1 mole per second, the volumetric flow rate comes out to be 5300 centimeter cube per mole. Once you know the molar flow rate and volumetric flow rate, you can able to calculate molar volume, which is the ratio of I have mentioned it wrongly. Okay, v dot, this is a volumetric flow rate divided by molar flow rate. Okay, Once you mention this volumetric flow rate divided by molar flow rate, you get molar volume, which is 5300 centimeter cube per mole at this temperature and pressure conditions. So these are the hand calculation methods. Okay, we will come up with the hand calculation method later. Okay, let me take you. Let us put these values. Let us use the DWSIM. Let us see how much amount of molar volume we get from the DWSIM method. Okay, so one second. Let us go to the DWSIM. Turn on the DWSIM. It is the same method we are following, and create new simulation, and there will be options that will come up. So you need to insert component, n-Butane is the component, is already visible here, so you don't need to search for it. And n-Butane, but then it comes to the one is Raoult's law. That means if you wanted to find out the ideal molar volume, you have to use Raoult's law. And if you wanted to find out the real gas volume, there are number of methods are there. One such a method is Soave Redlich SRK method. So these two are selected at this moment, and the rest of the things keep it as it is. And finally you find out the unit system you are interested in. I'm let us say the temperature is in Kelvin, the pressure is in bar or Pascal, whichever is interested in. Mass flow rate I'm interested to see in kg per second. Molar flow rate all moles per second. Okay, and volumetric flow rate centimeter cube per second. Okay, so these are the minimum units you have to mention before you proceed, and rest everything you can keep it as the same. So let us move further. Molar volume anyway it is supplied. No, you don't need to worry about this, we will calculate. Okay, next, and may set the simulation ready. And here what you have to drag here. So let us drag one material stream in which the material is as such flowing. Okay, material stream that is flowing. Okay, double click on this material stream, mention the temperature, like how much is the temperature, 350 Kelvin, 350 Kelvin, and the pressure is 5 bar. Okay, and moles per second is I'm interested in per mole basis, so I keep 1 mole per second. Okay, let us compounds. If you check for the compounds, the compound is n-Butane we have selected, and the compound percentage is 100%, which is you can say mole fraction is 100%. And you check for the property packages. We have selected two property package. One is Raoult's law and Soave Redlich Kwong equation of state. So let us select for the SRK method. Okay, select SRK, and once it is done, and let us find out what is the molar volume. In results, you can check, and let us display a few things here. So insert property table. Okay, in stream number 1 I am interested in showing molar flow. Okay, volume flow. Let us make it possible. Okay, now you can see that the flow sheet, I mean the moment you put the the moment you put the conditions, the flow sheet will automatically be calculated. If you wanted to re-verify, simply click this solve button, and you are going to uh, get the flow sheet solved. So you can observe here what presently SRK equation has been used. Okay, what is the volumetric flow you have got? 5300 centimeter cube per second. What is the molar flow you have used? 1 mole per second. Now volumetric flow rate divided by molar flow rate, if you do that, you are going to get the value of the molar volume of n-Butane at this present conditions is 5300.85 centimeter cube per mole. Okay, first of all we need to check whether at this temperature and pressure conditions n-Butane is existing in the vapor or a liquid. Okay, to do for that, let us input other parameters like molar fraction. Type in the molar fraction of the vapor, simple click, Okay, you can see in this at this conditions, whatever the material is there in this material stream is completely vapor. That means whatever the molar volume you are going to find out, that will be for the vapor. That means at temperature 350 Kelvin and pressure is equal to 5 bar, according to the SRK equation of state, the molar volume of n-butane is 5300.85. Okay, what will be the ideal volume? Let us, if you simply change the property package to the Raoult's law, automatically you can check that molar volume of n-butane, if it is behaving ideally, it is around 5819.8. Okay, you can see the volume, the SRK volume, molar volume is less than the ideal volume because of the intermolecular forces of attractions. Because ideal gas, I mean, ideal gas came up with some assumptions because there are no intermolecular forces of attractions, and there are the molecule volume itself is negligible. Okay, but the other models came up with the relaxing these assumptions. That why you are going to find out the ideal volume is higher compared to the real volume, because in reality molecules attract each other because number of intermolecular forces of attractions will make them come closer compared to the ideal gas. This makes, okay, ideal gas volume higher than the real gas volume. So let us proceed, with the hand calculation now. Okay, so this is how, and we are going to use a generic equation of state. Okay, this kind of equation Z. Okay, it's a compressibility factor. That means you are going to find out the volume using value of the Z. Once you know the Z, you can able to get the volume of the molar volume of n-butane. So there is an equation came up with in the textbook, chemical engineering thermodynamics by Smith and Van Ness, and you are going to see this kind of equation. Okay, the equation is used to predict, okay, compressibility factor of gases. This form of equation you are going to see especially used for vapors. Okay, this particular equation is called generic equation of state. That means any equation of state can be extracted from the generic equation of state by using appropriate values of the parameters. For example, this equation, if you take the values of, you can able to see the sigma equal to 1, epsilon equal to 0, omega equal to 0.08664, psi equal to 0.42748. If you can able to put these values in this equation, then this equation transforms to SRK equation of state. You can see the value of alpha, how beta can be computed. You can omega into PR by TR, Q can be computed by psi into alpha of TR come omega by omega into TR. TR and PR are reduced temperature pressure and reduced temperatures. So given all the parameters, if you can able to solve, you get the value of the compressibility factor. Once you get the compressibility factor, okay, you can see Z equal to PV by RT. Therefore volume, molar volume is nothing but Z into RT by P. So finally you are going to get molar volume of n-butane using SRK equation of state from the generic equation of state. So the conditions we have used, that temperature equal to 350 Kelvin, pressure equal to 5 bar, R equal to 8.314 joule per mole Kelvin. The TCPC, the critical temperature and critical pressure values will be, you can able to find out in the textbook itself, which is 425.1 Kelvin and 37.96 bar. So putting all the things, you can see, let us solve this equation. This, you can see, this is an implicit equation. That means you have to find out, make sure on the left hand, I'm sorry, on the left hand side keep it as zi plus 1 wherever z is there. On the right hand side wherever z is there keep I. Now now it will be in the iteration mode. Now you can able to solve this equation to find out the value of z by initial guess value. Assume the guess value which is 1. Because z equal to 1, the compressibility factor for the ideal gas PV by RT is always 1, because PV equal to RT, z equal to PV by RT, which is equal to 1. The best possible guess value we can give for the value of z is 1. So by putting the value of z, compute zi plus 1. Okay, now these both are not matching. That means the assumed value is not equal to the actual value. Now keep it as a second assumption. Now assume 0.920849 in this equation. Find out again, compute the value of zi plus 1. Now you can see, now they are getting very closer. Now keep this as a new guess value, compute the value of zi plus 1. Finally, if I consider the two decimal points, the 0.91 and 0.91 almost close to each other, that means I can stop the iteration. The solution for this equation, for the n-butane, the value of z is 0.912265. Okay, once you got the value of z, compute the value of v, which is equal to zRt by p. You get the value p. You can see, because you have to use SI unit, so I have converted to Pascal here. Because 5 bar, 5 bar is nothing but 5 lakh pascals. So once you've done it, you can able to find out the volume. So finally the volume you are able to get is 0.00531 meter cube per mole. If I able to change the unit systems, the volume from the molar volume of n-butane from SRK equation of state is 5309.202 centimeter cube per mole. Now you can verify how much close we have got. So let us see if we can able to check. Now you can check SR 5300. Okay, and through the hand calculations we have got very close value 5309. Okay, the molar volume of n-butane. Let us compare with the ideal gas. Raoult's law, if you keep the Raoult's law, the ideal gas value, it is close to 5800.19 centimeter cube per mole. So now let us see, because let us assume butane and butane gas is behaving ideally. So for ideal gas, Z equal to PV by RT equal to 1, therefore volume is equal to RT by P. So from that, if you compute the value of volume in the units we require is 5820 centimeter cube per mole. You can see the difference between these two. Okay, compared to the volume predicted by ideal gas, volume predicted by SRK model is less, because of course it will be less because the intermolecular forces of attractions and makes the volume more compressed compared to the ideal gas. So when you talk about the difference between the real gas and ideal gas, real gas means prediction from that equation of state, which is SRK. So if you compute the residual volume, that means the difference between the real volume and ideal volume, it is nothing but V from the model minus V from the ideal model. V from the model, because we have used SRK model, so the real gas volume as predicted by the SRK is 5309.202 minus ideal volume predicted by ideal gas equation of state, which is 5820. So the residual volume is minus 510.598 centimeter cube per mole. So this is how okay, this is how we can able to deal with the systems. Okay, thank you very much. Let us meet with the new lecture.